The second nice result is implementation of what I'm just erasing right now. Not only is Floquet multiplier the same computed any place in my coordinates for my periodic orbit, but in Japan they'll get the same multipliers, even though they use totally strange coordinate system where they've used Mayer-G and hypergeometric transformations to go from my stupid coordinates to the very elegant coordinates. So, okay, multipliers, invariant, and the huge group of transformation, which is, the general group of transformation general relativity, all smooth conjugacies. Now this is much more ambitious than you changing coordinates by rotating them by 45 degrees or going to polar coordinates. This is all possible transformations which are not mutilating the dynamics. They're smooth enough, so dynamics is the same in different coordinate system. So here we are. I have a function, I have a set and a mapping. So my dynamics is defined as state space and law of dynamics on it. But your dynamics is defined as m tilde g. So you have a different state space and you have what looks like a different law of evolution written in your coordinates. And they're related by y is h of x. To be very lazy, suppose that our state space was one-dimensional and this dynamic was just mapped from a line onto itself. So for example, you take a point on a line, you square it and add 3. That's an example of using a nonlinear map on the interval. And this is parabola, so you can take square roots of it. So you can go back and forth and define mapping both ways. Simplest possible example. And now what you would like to know is if you have a fixed point in your original system. So if your original function was f, and this is where you are at time n, and this is where you are at time xn plus 1. So you have simple 1D dynamics. xn plus 1 is function of xn. Then the fixed point, xq, will satisfy that you're there forever. So this is your fixed point, xq, in your original coordinate space. And we are studying Jacobians. Jacobian is the derivative of, where you are at later time to previous time, and that derivative is just the slope. So Jacobian, it's 1-by-1 matrix. So you can just write it as a multiplier. Evaluate it at the fixed point q. So now in Japan, they have a different function g, which is obtained by replacing my x by h of x. So to me, it's not obvious that they will find the same stability in Japan as I find here. If I have this relation, then this map G and the map in Japan can be written in the following way. I want this to be function in y space because, all the points here are y points, elements of tilde space. That means that I want to look at g of h, and I'll just write the result. The map in this space is obtained by going from y coordinates to h coordinates, which is h minus 1, using the result as the argument of the function in this space, and then going back from x coordinates to y coordinates. So if it were just rotations, what we would do is we would first, rotate from x back to y, so we have to go counter-rotate, then we would do whatever we do in our lab frame, then I'll rotate it back. But the relation is actually a functional relation. In that case, I would have product of three matrices or something. But in general, I go from y to my coordinates here. I apply my law, which is a mapping of x. So this means I'm looking at f of x. Then I've gotten my result of my f operation in my coordinate x. So to come back to the y world, I have to change coordinates again, right? So this is h of f of, and x itself is h minus 1 y. So are you happy now? But it's, more elegantly written as a functional composition. So now I'm still in one dimension, and my question is, in my new coordinates, in this world here, what is the law of motion in the new coordinates? And the fixed point in the new coordinates should be someplace on the diagonal here. So this is yq, which is the image of x in Japan. And I would like to know the slope, g prime evaluated yq. I take derivative with respect to y of both sides of the equation. So I'm interested in g prime, which is d dy of h of f of h minus 1 of y. And now I can use chain rule. This is a function of a function of a function, so it'll be product of three derivatives in a chain rule. So the first one is derivative of h with respect to, h is this map here, so it has to be with respect to its argument, which is where I'm in this space. Evaluate it at f of x, but I'm at a fixed point, so this is evaluated x cubed. This has to be multiplied by chain rule by derivative of f with respect to its derivative. So this is evaluated at x, and I want to evaluate this as a new point. And then I have to take derivative of d dy of h minus 1 and evaluate at yq. This object is 1 over h prime. These two guys cancel, and we prove that the slope of the map gyq equals the slope of the initial map computed at x cubed. In other words, multiplier of 1 by 1 matrix, Jacobi matrix J, is lambda and invariant. To me, this would not be obvious because functions look totally different. A fixed point is a different place, etc. And the reason why it's true is this rubber sheet argument from before. When you're looking at the neighborhood, you're looking at any interval divided by what is it after one iteration. If you stretch the neighborhood, you'll multiply both infinitesimal intervals by the same deformation number, and they'll cancel out. This invariance doesn't know about length. This is just intrinsic to dynamics. We have never defined notion of length and norm. To you, it might seem trivial, but later on, what is norm is totally not obvious.